Okay, can you hear me and see the slides?
Yes, perfect.
Okay, okay, great. Okay, so the relationship of scientists and physicists in particular to nuclear weapons at the beginnings of the nuclear age is very, very well known, very well studied, very well popularized in books and movies and everything. But today, the relationship of scientists to nuclear weapons is also extremely critical. And so the focus of my talk will be the relationship today between scientists and nuclear weapons. And oops, let me see if it, there we go. So scientists interact with nuclear weapons in two different ways. One is in favor of nuclear weapons. Scientists participate in research and development to advance nuclear weapons. On the other hand, scientists also work against nuclear weapons through advocacy and activism. And this has been true in the past, and this is true today. So these are the two roles. A lot of my discussion will be focused on physicists because physicists have been particularly involved in nuclear weapons, but the comments are really general. So let's first, before we talk about today, just remind ourselves about the past and how scientists have been involved in nuclear weapons in the past. So in terms of advancing nuclear weapons, clearly scientists and physicists in particular have played a central role in inventing these weapons and in further developing them. Physicists, after all, discovered and led an understanding of nuclear fission and nuclear fusion, both of which is included in a nuclear warhead. And they took this understanding to develop the implosion process, which underlies most of the nuclear weapons of today and beyond that. And this is very well known. The details of the Manhattan Project and beyond are well known, and I won't be talking about that further. But physicists also, since the dawn of nuclear weapons, played a key role in activism against nuclear weapons. And remarkably, this included many of the really great physicists, the greatest physicists of the 20th century. So before I get to today, I do want to just take a moment to review just a few, it's not comprehensive, a few of the actions that physicists have taken early on against nuclear weapons. And so let's talk about physicist advocacy against nuclear weapons. And let's begin with the 1940s. And Niels Bohr made personal efforts to meet with Churchill and Roosevelt to warn about a nuclear arms race. So that was unsuccessful, but he made personal attempts in that regard. There was a Frank report that suggested that the nuclear weapon, the bomb, not be used. He was against this report was against the first use of nuclear weapons in Japan, and instead it recommended that the nuclear bomb be demonstrated as a means to indicate its power. This was led by James Franck, who is famous for the Frank-Hertz experiment. There was a petition that was led by Leo Szilard, who discovered the chain reaction and played a key role in starting up the Manhattan Project. Anyway, he led a petition with 70 signers from the Manhattan Project to argue against the use of a nuclear weapon and to warn of a nuclear arms race. This was clearly was not followed. In the 40s, Albert Einstein and others formed the Emergency Committee of Atomic Scientists. This was a committee of about 8 scientists. You can see there's Einstein and also Hans Bethe behind them, and Victor Weisskopf and others. And this was actually formed in Princeton, and this emergency committee was formed to alert the public to the new dangers from nuclear weapons. Uh, in the late 40s, there was a Atomic Energy Commission in the United States advisory committee that was asked to make recommendation regarding the developments of the hydrogen bomb that included fusion. It was chaired by Oppenheimer. And that committee recommended against developing hydrogen bombs, and they mentioned that this would lead to a policy of exterminating civilian populations. The committee included Fermi and Rabi, and they issued a minority report where they said that this weapon in practical effect is almost one of genocide and is necessarily an evil thing considered in any light. Unfortunately, this recommendation also was ignored. You move on to the 1950s, Einstein was outspoken. For example, Einstein wrote that the scientist, and to quote him, degrades himself to such an extent that he helps obediently in the perfection of the means of the general destruction of mankind. In Germany, there was a Göttingen Manifesto where 18 German physicists opposed Germany developing nuclear weapons, and they stated that they would not participate in the creation or deployment of nuclear weapons. This included Heisenberg, Born, and von Laue. This actually was successful. In the 1960s, there was a petition to end nuclear testing, which was signed by 9,000 scientists from 43 nations. It was led by a chemist, Linus Pauling, and here you see Pauling protesting in front of the White House against nuclear testing. And I believe this is the year he won the Nobel Prize in chemistry. And that evening, he was going in to dine in the White House. So he protested in the afternoon and went to dinner in the evening. In 1995, Hans Bethe, a physicist Nobel laureate who was also the head of the theory group in the Manhattan Project at Los Alamos, he made a statement where he said, I call on all scientists in all countries to cease and desist from work creating, developing, improving, and manufacturing further nuclear weapons. So he called on all scientists to simply not work on anything related to nuclear weapons. A very powerful statement from someone who worked on the Manhattan Project. It's interesting to note that almost all of these above outspoken physicists were European. Many of them had emigrated by necessity to the United States, but it's remarkable that they were mostly European physicists. Well, what about today? And I'll come back to this at the end of my talk. Today, by contrast to this, there's relative silence in the physics community regarding the problem of nuclear weapons. Advocacy against nuclear weapons by the scientific community. I'll use physicists, scientists interchangeably. Advocacy by scientists against nuclear weapons is weak today. Also, discussion and the questioning of the ethics of nuclear weapons work that was struggled with by people like Einstein in the early days. Well, such questioning and discussion also is highly muted these days in our community. And it's clearly given that the danger for nuclear weapons is as severe, if not greater than any time in the past, it's now time to renew this discussion within the physics community and science community, and also to accelerate advocacy. So this is all I want to say about the past. And now let me move on to the present and physicists and nuclear weapons today. Well, today, physicists play a central role, as they always have, in the further development of nuclear weapons. And I'm going to, and I apologize for being a bit provincial, but I'm going to be discussing a US example of what's called the Science-Based Stockpile Stewardship Program. And I think it's probably emblematic of physicists and scientists work in other nations on nuclear weapons, but I'm going to focus on this because it's a relatively transparent program. It's written about, and we know most about that, and then more about that than analogous programs in other countries. And after all, the U.S. with Russia owns most of the nuclear weapons in the world. And then also, I'm going to make a case at the end that the physics community should discuss the consequences and ethics of research related to nuclear weapons. And regard to advocacy, I'm going to, at the end, just cite one example of a new organization that was recently established for educating physicists about the current threat and employing physicists for advocacy against nuclear threat reduction. And I'll spend just a little bit of time describing the Physicists Coalition for Nuclear Threat Reduction. So let me first talk about how physicists are involved today in advancing nuclear weapons. And as I say, I'll talk about the example of the US Stockpile Stewardship Program, sometimes referred to as the Science-Based Stockpile Stewardship Program. This is a program that was initiated in 1994 as an alternative to testing nuclear weapons. The idea is that if you have this science-based research program, that could replace nuclear testing. We can learn what we would from testing by science-based activities. The stated purpose is to assure the safety, security, and reliability of the U.S. nuclear weapon arsenal. By safety, they mean prevention of an undesired nuclear detonation, a nuclear weapon going off by accident. By security, they mean protecting nuclear weapons from unauthorized access or use. You can imagine a hacker getting in and into the nuclear weapons control system. And by reliability, or sometimes called effectiveness, it means the confidence that the nuclear weapon will perform as designed. It'll explode when and where you want it to with the appropriate yield. This is a big program. In 2024, it cost about 17 million US dollars. It's managed by what's called the National Nuclear Security Administration, housed within the Department of Energy. And I like to ask, we'll be asking the question, does the science-based the Stockpile Stewardship Program, the SSP, increase or decrease the global security of the world? Let me first describe very, very briefly the technical components of the scientific programs and components of the Stockpile Stewardship Program. It studies the science of the nuclear primary, the primary of the nuclear warhead, which is a fission explosion, and it's focused on the hydrodynamics of the nuclear primary. Basically, understanding the compression of the plutonium pit, that's the core of the fission primary. And this is done using surrogates for plutonium, compressing other kinds of metals, or compressing plutonium in subcritical tests where you don't get a supercritical chain reaction. There's also a large program in what is called high energy density physics, the physics of matter that's compressed so dense that the density of energy is exceedingly high, a very exotic state of matter. This is relevant to the fusion secondary, which includes nuclear fusion in addition to fission. It studies the propagating fusion burn, sometimes called ignition. It studies the compression of the secondary by X-rays, the implosion by bathing the fusion fuel in X-rays. This involves nonlinear plasma physics and also material properties. And let me just mention a couple of the facilities. This is not by any means meant to be exhaustive. To study nuclear primary hydrodynamics, that is the compression of the plutonium pit or other metals, there's at Los Alamos, there's a facility called the Dual Access Radiographic Hydrodynamic Test Facility, or DART, which is a big X-ray machine. It does X-ray imaging of compressed materials. And at this vertex here, there's an explosion, a chemical explosion that compresses a substance to a high density. And these two arms are two electron accelerators. The electrons smash into a target and release X-rays. So you get two-axis imaging of X-ray imaging of the compressed state of matter. In the Nevada nuclear security site, used to be called the Nevada test site, they do underground subcritical test explosions. To study high energy density physics, particularly relevant to the fusion secondary, there is the very well publicized National Ignition Facility at the Lawrence Livermore National Laboratory in California. And the basic idea is you have a frozen pellet of deuterium and tritium, that's the fuel for fusion explosion, and you bombard it spherically symmetrically with X-rays, very intense X-rays. The X-rays cause this sphere of fusion fuel to compress. As it compresses, it heats, and then you get a micro explosion. You get a propagating fusion burn, and you can study it. It's clearly relevant to a nuclear weapon. The technology behind this is quite remarkable. The little pellet is put inside a can called a hole realm. Through two holes, lasers are injected into the hole realm. It vaporizes it, converts to X-rays, and then the X-rays implode this sphere. And here you can see the scale of this little pellet of fusion fuel. The little pellet fusion fuel is put into a big vacuum chamber, and then it's bombarded by the biggest set of lasers in the world. There's football fields of lasers eventually focus on this little pellet, compress it, and you get a very momentary fusion explosion that can be studied. And the question is, does this research program increase or decrease the security of the US and the security of all worlds? And this is very relevant to the physicist's decision to work on this project. The core argument for the SSP is simple, that it enables the US to participate in the global ban on nuclear testing. That is, this program provides information that is otherwise obtained from testing, and even more because you can get really fine-grained measurements. And the global test ban, which was implemented around 1996 and incorporated into the Comprehensive Test Ban Treaty. Before 1996, there were over 2,000 nuclear test detonations. Here's one in the Nevada desert. So 2,000, and this is what enabled the world to advance nuclear weapons. After 1998, that number went down to 0, with the one exception of North Korea. This is a great accomplishment. And what does it do? It constrains the development of nuclear weapons by non-weapon states. If you can't test a nuclear weapon, it makes it harder to develop one. And it also constrains the development of new nuclear weapons or new nuclear weapon designs by existing nuclear weapon states. So it puts a bit of a brake on nuclear weapons developments. Doesn't solve the problem, but it helps not make the problem worse. And it's been successful as a moratorium. So the core arguments, just to repeat them, the first one is it enables the US to participate. It gives an argument that the US uses to itself to participate in the moratorium on nuclear testing. It assures the safety, security, and reliability of the weapons in the stockpile. In the US, it's also argued that it locks in the US advantage of having performed more tests than any other nation. The US performed over 1,000 tests, more than any other nation. So it has more data from testing, and this is argued in the US to be an advantage. So these arguments can appear to be benign. Even if you're against nuclear weapons, as long as they exist, you want them to be safe, secure, and reliable. And this has been appealing, and I think has drawn many scientists into this program. And these are all true statements, but it's hardly the end of the story. There are other factors to consider. And the first is that this core argument for nuclear testing is really a cheat. It really violates the spirit and intent of the global test ban and violates the intent of the Comprehensive Test Ban Treaty. And this is so obvious. It's because the US gains the knowledge that testing was meant to prohibit. It just does that without testing through science research. So it's kind of a workaround the treaty. So you don't have to test, but you still get all the knowledge that can accelerate the development of nuclear weapons. So it's a cheat. As I just said, the knowledge could enable new weapons development. This advantage of new weapons development is absent to nations that either do not test or don't have a comparable SSP. So it introduces a usual asymmetry and double standard that indeed could be destabilizing and could just help further fuel the nuclear arms race. At the inception of the SSP in 1994, if you think back to that time, it was a better time in a way from nuclear weapons point of view. It was a time of bilateral Soviet and US strategic arms reduction talks. And through the 90s and beyond, there was an 85% reduction in the nuclear arsenals in the US and Soviet Union. So it was a different time. It was a time of contraction of nuclear weapons. And it is true, I believe, when this program in the United States was initiated, there was no intent to develop new nuclear weapons. And in a strategy document, an official strategy document, it stated that no new weapons are being designed, and I trust that was a true statement. On the other hand, a strong research program was initiated that could produce new weapons if it was ever needed in the future. And in that same document, it's stated that stockpile assurance will require breakthroughs in science and technology. If you're not testing and you want to assure reliability of the stockpile, you need breakthroughs in science and technology, it was stating. And a report called by a group that's referred in the U.S. as a Jason group. It's a group of scientific experts in nuclear weapons, but not part of the nuclear weapons program necessarily, that meets to assess technically issues related to nuclear weapons. And that even in 1994, these scientists in the US stated that the SSP may be perceived by other nations as an attempt by the US to continue the development of ever more sophisticated nuclear weapons. So even though there may not been an intent in 1994, clearly the seeds were set to develop new types of weapons if needed in the future. So if you look at today, well, is this introducing new ideas for weapons? And the answer is probably yes. The geopolitical landscape now is much more adversarial, and we're now in the midst of a new nuclear arms race. In fact, in the 2018 U.S. Nuclear Posture Review, an official document from the U.S. government, it states that the need for flexibility to tailor U.S. capabilities to meet unanticipated developments runs contrary to a rigid policy of no new nuclear capabilities. Kind of a convoluted statement, but it says that the U.S. has to be able to be flexible enough to develop new nuclear capabilities if needed. Also, it's often stated that if you want to train and retain the next generation of bright nuclear weapons scientists, well, you're not going to do that by just giving them the job of maintaining an existing stockpile. You have to allow them to design novel warheads in order to keep an innovative scientific staff. We can also recall that a majority of the nuclear weapons tests of the past prior to 1996 were, in fact, not to assure the reliability of the stockpile at the time, but in fact were to develop new designs. Only a modest number of those tests were confidence building in the reliability of the stockpile. So there's every reason to believe that the present stewardship program can lead to the development of novel designs for nuclear weapons. And this has destabilizing consequences. Other nations might well assume that the US is developing new weapons ideas and will respond in kind. And it's kind of, I don't know if amusing is the word, that there were just this year, there were satellite observations, images taken by satellites viewing China. And here is a report from Reuters, news agency. It says exclusive, images show China building huge fusion research facility, analysts say. And you can see here, there's what they identify as laser bays and a target chamber. And in the article, it says this new Chinese facility could aid nuclear weapons design. It's important since full nuclear testing is banned. And it says the experiment bay where this is held in Mianyang is 50% larger than the US National Ignition Facility. So this facility that's sometimes treated as a science facility in the US, here it's kind of revealed, it's revealed through satellite images, and it's treated purely as a military asset, as if you were seeing a new ICBM field. So this kind of, I think, is consistent with these kinds of science research programs being destabilizing and proliferative. Now, you could also ask the question, is testing needed even if one didn't have a stockpiled stewardship program? And this leads to the question of what does reliability of nuclear weapons mean? It sounds very benign to just assure that a weapon is reliable. What does it mean? And reliability means, it refers to the likelihood that the weapon will deliver the specified yield on the target at the specified time. So this involves, launch and delivery and the detonation time and the yield. One wants all that to work as designed. If you focus on the warhead, which is sometimes referred to as the physics package, where a lot of the physicists are focused, unclassified reports indicate that reliability is taken to mean confidence that the warhead yield, the explosive energy, will be within 10% of the design value. So if it's designed for 300 kilotons, you want it to explode within 10% of 300 kilotons. That's what's meant to be reliability of a warhead. On the surface, this sounds reasonable, but if you think about it for just a moment, you realize that what does reliability of a nuclear weapon mean? It means really nuclear weapons are meant to deter a nuclear attack by an adversary. So really the real reliability is the reliability that a deterrent is credible to an adversary. So it's partly a psychological assessment of the psychology of the adversary. This is impossible to quantify. And also, it almost seems hard to imagine that any adversary would ever doubt the reliability of US nuclear weapons with or without a stockpile stewardship program. And the reverse is also true. I can't imagine the US would ever doubt the reliability of a nuclear weapon coming from North Korea or Russia or China or anywhere. So it seems that reliability as a technical measure loses all meaning when it's applied to the technical system of nuclear weapons. It seems a silly thing to worry about, almost absurd, and also absurd to apply a technical metric to it, quantitative metric to it. So is testing needed without a strong SSP? Well, most other nations have concluded no. Only a few handful of nations have stewardship programs, and to our knowledge, none of them are yet as strong as that of the US. The one exception is North Korea. China and Russia and France have stewardship programs. The UK, to some extent, as I say, although I think they're weaker than that of the US. France does have a experiment analogous to NIF, the National Ignition Facility. It's called Laser Megajoule experiment. It's not quite as far along yet. But the vast majority of nations in the world neither test nor have SSPs. So this is the usual double standard applied to some nuclear weapons possessing countries that they say they need such a thing. So the U.S. stance is, well, singular may be too strong a word, but it's a little bit exceptional. And as I say, it's consistent with the U.S. with the usual nuclear double standard. So having settled this, what's the net effect of stockpile stewardship on global security? And one good thing is that it provides a rationale within the US system to forgo testing. So even if you think the argument isn't a sound one, it actually works within the US and it's accepted by the US government and therefore there's no testing. That's good. But what's bad is it violates the intent of the test ban. It maintains the nuclear double standard that this is good for us but not good for others. And it encourages a proliferative response in other nations. And I think we're seeing that in these observations over China. In the Department of Energy written management plan for the stewardship program, it stated that the stewardship program must be capable of serving the stockpile for the next 50 years or more. This is a sweeping statement, and I think it indicates clearly that the stockpile stewardship program, summing all of these factors in, the bottom line, it advances the salience of nuclear weapons in geopolitics and in warfare, and that's a bad thing, and should be considered by any scientist working on this program or thinking of working on this program. I think I'll skip this. And so you can ask the question, should scientists work on this program? And the program in the US employs about 7,000 scientists and about 13,000 engineers, mainly at the three weapons laboratories, Los Alamos, Livermore, and Sandia. And let's consider the example that I've discussed of the National Ignition Facility. Why do scientists work on NIF? And there are several reasons. One is for fusion energy. It gives information that is useful for the development of fusion energy for completely peaceful use as carbon-free energy. This is a very strong motivator for scientists to work on in this program. It also offers fascinating fundamental science on extremely compressed matter. And it also offers opportunity for technological development, particularly in optical science. And these three reasons probably not only, they surely attract many, many physicists to NIF. And I don't have data, a survey to prove this, but I think it probably attracts most of the physicists to the National Ignition Facility, particularly the peaceful energy application of fusion energy. and this surely attracts most of the press attention. It's quite remarkable. And in 2022, when NIF achieved ignition, more energy out, and went into the capsule, this attracted worldwide press attention as a step forward for fusion energy. And most of the articles ignored the fact that it also contributed to nuclear weapons science. And in fact, the fourth reason for NIF, for nuclear weapons, is the reason that this is funded. It is not funded for any of the other three categories. Those are all collateral benefits. It is funded exclusively to advance the understanding of nuclear weapons. So should physicists work on NIF? My personal answer, of course, is no, because I think it's endangering, but it's something that every physicist should answer this question for themselves, considering all the above. And this should be discussed actively in the physics community and within the public. And it is not being discussed actively in the physics community. And so this is one conclusion, is this should be discussed. Now, let me close with moving beyond physicists' technical involvement with nuclear weapons in ways that advance it to physicist advocacy against nuclear weapons. And I'm going to talk about this one example that I'm involved in, called the Physicists Coalition for Nuclear Threat Reduction. And it was established 4 or 5 years ago. The goal is to engage the physics community on this problem. The physics community is also significantly tuned out to this problem, like the general public is, and to mobilize the community to advocate against nuclear weapons development and use. It was developed a little bit with the idea of the cliche of think globally but act locally. This is a global problem, and locally usually refers to someone's geographic location, but for scientists, local means their scientific community, which is worldwide, but it's topically local. So local to us is the physics community, and we started with the US physics community. By ACT, we want to engage and educate the physics community on nuclear weapons issues and mobilize it for advocacy. The premise of establishing this is that the physics community, because it has a special relationship to nuclear weapons, and that relationship is strongly appreciated by the public and stakeholders, can add a unique and influential voice to this debate. This was formed in 2020, and it was founded at Princeton University, but it's national, and it was started with support from the American Physical Society. Our mission statement is the coalition works to reduce the threats by mobilizing advocacy within the physical science communities in the US and internationally. We advocate for substantive changes in arsenals, force postures, and declaratory policies. And we also call for fulfillment of the longstanding international obligation to achieve nuclear disarmament. And how do we do this? First, we have to educate and recruit scientists to the coalition. And we do this through a strong grassroots effort where we have a team of 15 physicists with expertise on these issues, and we visit physicists where they work. We go to physics and nuclear engineering departments and national laboratories, and we present a colloquium that overviews the whole problem of nuclear weapons and engages in discussions. In the last few years, we visited about 170 sites all across the US and into Canada. We've recruited 1,700 members to the coalition. We've probably made presentations to about 20,000 scientists through all this. And we also have a next generation fellowship to recruit young people. We do advocacy. We treat these 1,700 members as physicist citizen advocates. Not all of them do this, but a fraction do. Among our advocacy techniques, once a year, we bring about 30 coalition members to Washington, D.C. for a day of training and 2 days of lobbying. We visit about 50 congressional offices. Here are some of our past lobbying goals. We've lobbied against what's called the Golden Dome missile defense system. We lobbied against that, lobbied for a follow-on agreement to New START, for elimination of the ICBM leg of the triad, for consideration of war planners of the full consequences of nuclear weapons use, including climate effects and societal breakdown effects. We've argued against the development of a sea-launched nuclear cruise missile. We've argued for a no first fuse policy, against planning for resumption of nuclear testing, and more. I know clearly this is very, very, very difficult in the present political landscape of the US. We're beginning to engage internationally. We want to establish links to other nations, and we are currently successfully expanding our visit program of colloquia into Canada. That's going pretty well. 2 years ago, we held a international workshop at the Center for Theoretical Physics in Trieste, Italy, uh, called The Increasing Danger of Nuclear Weapons, How Physicists Can Help Reduce the Threat. And we had 50 attendees from 20 nations. And so we're trying to stimulate activity similar to what we're doing elsewhere. And we're beginning outreach to Europe, which is so relevant because the NATO nations are in nuclear alliance with the US. They fall within the US nuclear umbrella. And of course, Europe contains two nuclear weapons states. So we think there's a strong opportunity for collaboration between scientists in Europe and in the US in joint advocacy, in the education of physicists on this problem, however it's best to do that. And the coalition can certainly offer to give colloquia. So there's a lot of opportunity that's untapped, but important to maybe to initiate collaboration between scientists in Europe and the US on this problem. So to close, I'll say that physicists continue to be critical to the further development of nuclear weapons. Unfortunately, I gave the example of the stewardship program, and we need to do more in advocacy. And I've just described a new organization. Yeah, these are the conclusions. So the role of physicists in advancing nuclear weapons really needs to be highlighted and discussed in our community. And we hope to coordinate with European physicists in the near term. So with that, I'll close and say thank you for listening. So maybe I'll.
Thanks very much, Stuart, for this very interesting and excellent talk. Thanks very much, Dean. This was really very good. I stop now recording and open the discussion.